Okay, welcome back, everyone. So now it is my great pleasure to introduce Deepak Vij, and he will present the Centaurus distributed cloud infrastructure from FutureWay. So Deepak, please, the floor is yours.
Great, thanks, Thomas. Can you guys? I shared my presentation. Can you see it?
Yes.
Okay, great. Yeah, hello everybody. Good morning or good evening, wherever, depending on where you are. Yes, I'm Deepak Vij. I'm part of FutureWay Cloud Lab. I'm a researcher and a cloud strategist based out of Santa Clara, California. So in so how much time do I have, Thomas?
We allocated 20 minutes.
20 minutes, great, okay. Yeah, so I have about 30-odd slides, so I'll try to squeeze them all in 20 minutes. So I'll be providing a deep dive into Centaurus distributed cloud infrastructure platform we've kind of built out, and then donated this project to Linux Foundation about a year ago. Okay. Yeah, so as I mentioned, Project Centaurus, we've been working on this project. Our team, Research Lab, Cloud Research Lab, has been working on it for the past couple of years. And we completed that and then donated this project around about a year ago, actually, in December, early January timeframe last year. So Project Centaurus and donated that project to Linux Foundation. So it's this open source Linux Foundation platform, and it's targeted towards building unified and highly scalable public or private distributed cloud infrastructure. Keep in mind this whole distributed cloud infrastructure, and I'll get into that actually. So it's not just one giant cluster cloud, but if keeping the edge cloud in the mix, how would you kind of all manage thousands of clouds as part of your cloud infrastructure? So that's the distributed cloud infrastructure I'll be kind of talking about. And it aims to meet the challenges for new types of workloads such as AI, 5G, and application landscape. Now, we all know that the characteristics of AI and 5G applications are very different than a typical central cloud environment. The low latency, need for low latency, mobility, location awareness, privacy, and security. These are the characteristics which you don't typically need need to address that as part of the centralized cloud environment. So the challenges are really very different. So that's what our intent is. As part of the distributed cloud infrastructure, we are addressing all of these needs to be able to support such application landscape, and offers enterprises the hyperscale-like capabilities that dramatically change it. So the key thing is the current state-of-the-art infrastructure, open source projects, OpenStack or Kubernetes, they don't kind of measure up to the hyperscaler level scalability and the whole unified cloud platform. So with our Centaurus, one can, enterprises, big enterprises, take this open source project and build out a public cloud scale cloud capability as part of their IT. So that's the kind of the whole value proposition why we built all this. And then the Centaurus by itself is an umbrella project, actually. So it's just like OpenStack. If you folks are familiar with OpenStack, it's an umbrella project, and underneath that we have just like OpenStack has Nova and Neutron and a bunch of other tons of other projects. So Centaurus is an umbrella project as well, and underneath that we have sub projects such as Arctos Compute, Mita Networking, Fornex Edge Computing, and then we have Alnair AI workload, AI platform for managing AI workloads. So we'll get into all of these. So the first I'm going to cover is the Octos compute sub-project as part of Centaurus. So Octos is an open source. This is a sub-project again. It's an open source project designed for large-scale cloud infrastructure. And it was, so instead of kind of building all this from scratch, we found that Kubernetes is a good starting point. And so essentially what Octos, what we have done is it's evolved from Kubernetes code base. And we had to do major surgery in order for us to be able to enable the hyperscaler level cloud infrastructure. But the key thing is it uses the same abstractions, the same API objects such as pods and replica sets and deployments and all that, which Kubernetes uses, and everybody is kind of familiar with that. So Kubernetes is a starting point for us, and then we extended in a major way to be able to enable a lot of new functionality, basically. So as I mentioned, we had to do major surgery, major enhancements to the upstream Kubernetes to enable the key capabilities of our platform, which you don't find that in Kubernetes or OpenStack. This whole unified cloud infrastructure resource support. So we'll get into that, what that is. And then the high throughput and low latency, the scalability aspect of our platform. And then the built-in multi-tenancy, hard multi-tenancy support, as part of the Centaurus platform. So these are the three pillars, actually, three key capabilities which we enable, which you don't typically find that in a state-of-the-art open source project such as Kubernetes or OpenStack or others. So that's what happened? Okay, yeah. So that's now the first thing I'm going to talk about, those three capabilities which I talked about in a previous slide, the scalability aspect of that. So this is kind of a high-level pictorial of what we have done as part of our Octos compute infrastructure. So as you can see that we have partitioned the Kubernetes. If you're familiar with the Kubernetes control plane and data plane architecture, we have partitioned the control plane at every level, actually. So that allows us to be able to scale and don't have a single point of failure as well. Because if you're building a large scale cluster, so you want to ensure that there's no one single point of failure that brings the whole cluster down. So essentially, by having this partitioning, we are able to achieve both the scalability as well as the fact that there's no single point of failure anymore. So if your one tenant partition goes down or one resource management resource pool goes down, the cloud is still up and running. So there's no a single point of failure. So as you can see that in a slide, that we introduce new constructs, as part of our Octos compute framework, such as tenant partitioning, resource managers. So these are the new abstractions for us to be able to define partitioning and the multi-tenancy from ground up. And then our goal is just to give you folks a baseline. The OpenStack or Kubernetes, they can typically, OpenStack can typically scale up to about 5,000 nodes in a cluster. And Kubernetes can scale up to maybe 10,000 or 15,000. And our goal is much higher. Because if you're building a hyperscaler level public cloud scale cloud platform, you should be able to have 300,000 nodes, physical hosts in a cluster, in a per region. So that's what our goal is, actually. So that's why we had to do kind of major surgery and all partitioning at every level data plane as well as control plane level to be able to achieve this, this goal. And these are all scale out and highly available. Tenant workloads are partitioned. So essentially what that means is they can scale out depending on the load in the system, and they're highly available. So if one tenant partition goes down, the cluster still works. You know, rest of the tenant partitioning still works. So there's no single point of failure. And then the tenant workloads are partitioned. So multi-tenancy is kind of built in as part of our platform. So the multi-tenancy is the second key aspect of our platform. So multi-tenancy does not exist in Kubernetes, actually, you see, and similarly in OpenStack as well. So we had to kind of do major enhancements to be able to enable real hard multi-tenancy, whereby you can have multiple customers essentially running in a same one cluster and totally isolated from each other. So the whole concept is that we have a tenant ID assigned to each tenant, and that kind of flows through the whole system. So all the APIs and the namespace aware APIs in Kubernetes and the system level non-namespace scoped API. So the whole tenant ID flows through the entire system, and that enables this hard multi-tenancy. So that's the kind of a very high level kind of a description of it. It's pretty complex, you know, there are a lot of information on our website, but that's what I wanted to kind of highlight, that, you know, what we have to do in order for us to enable hard multi-tenancy as part of our Octos platform. The key feature which we enable is a unified runtime orchestration. So essentially, you know, Kubernetes is very good at orchestrating containers, and OpenStack is very good at orchestrating VMs. But what if, you know, typically enterprises, big companies, or any company for that matter, you don't really use strictly containers or VMs. You use both, depending on the workload types. So, and the problem currently in a state-of-the-art projects, open source projects, is the fact that you have to use one platform for managing orchestrating VMs and another project, Kubernetes, for example, for managing your containers. So so what we've done is, as part of Octos, we've unified all of these different workload orchestrations, and with the one set of API, with same common API. Doesn't really matter if the workload is VM or a containers. You use the same API to orchestrate your workload, and tomorrow WebAssembly or unikernels using the same set of API space. So it's a unified runtime orchestration, which currently supports VMs and containers, but in future can be easily the new workloads can be easily plugged in, you know, the WebAssembly or the unikernels as well. So that's the kind of a key goal for us. Now the meets are so that was the very high level overview of what the Octos Compute is, and the next sub project is meets are networking. So meets are networking is a network virtualization layer for our hyperscaler next generation Centaurus cloud platform. The large scale cloud platforms such as Centaurus, they need to be able to scale up to 100,000 or 300,000 nodes in a cluster. And then the workloads are not static. They're not, you don't deploy a VM you know, maybe every couple of hours or so. Here the workloads are so dynamic. You know, you imagine you have serverless workloads, they come and go, you know, in a fraction of a second. So you need to be able to provision networking in such an environment. And then so the current contemporary open source platforms do not provide such capabilities, such dynamic workload provisioning of networking in such an dynamic environment. So that's why we had to kind of build the network virtualization layer from ground up, and that's what meets our networking is actually. So So what are the problems? So why didn't we use OVS? So I'm pretty sure you folks are familiar with most of the cloud platforms. They use OVS, the Open vSwitch, virtual switch. So and they're based on a flow-based programming model. So in a typical environment, OpenStack or where you use OVS, you have a control plane that programs your flow tables on each virtual switch on each host using OpenFlow protocol. So that's where the problem is. The current flow-based programming models are not scalable and have a multitude of issues and quirks. So one of the example I can give you is, what if your subnet is across maybe, for example, in a much bigger, large-scale enterprise environment, you may have a subnet that spans across 10,000 nodes. So now, let's say you add a new node in that subnet. Now you have to go and update all of those the flow rules and all of those 10,000 previous nodes to be able to include that new node as part of the subnet, basically. So that's the kind of a major problem, scalability challenge as part of the flow rule-based programming model. So as I mentioned, time to for provisioning ports increases significantly as the number of ports increase. As you add new nodes in a subnet, for example, if you're adding a new endpoint, it's gonna the provisioning is gonna take a lot more time, basically. So you have to, because you have to go around all of the hosts. And CPU utilization during flow passing is a major issue as well. And the packet traverse multiple network stacks on the same host. They have to kind of go through the Linux bridge and the OVS bridge and all that. So that's where, so all of this contributes to the fact that provisioning takes a lot of time, and provisioning time of a new workload depends on the number of workloads already existing in the system. So, so none of the current platform, the network virtualization solutions can scale up to this this challenge, basically. So we had to kind of build the network virtualization from ground up, and that's what meets our is actually. So we essentially moved away from flow rule-based model, network virtualization model, towards, and we'll talk about that, what that is. So XTP. So XTP is a new, it was introduced around 2018. So meets our networking is based on XTP protocol. It's the kernel bypass. So essentially it's not, it's a bypass in the sense that you do all your packet processing at the device driver level itself. So without even touching the kernel networking stack, actually. And then, so it's one of the good thing is XTP can be easily offloaded to a SmartNIC hardware environment. So which makes it highly efficient and much performant, actually easy. So that's, I'm not going to get into a lot of detail, but XTP allows us, that's the kind of a core of our network virtualization layer. And XTP is essentially a 4K eBPF set of instructions, which allows us to extend the kernel behavior and then do the packet processing much more efficiently. So that's the kind of a key thing to highlight that. So so that's so XTP. What we have done is, so that's kind of a high-level pictorial of what MEETSAR is. So essentially, we have two programs, on each host. One XTP program attached to the NIC, and it processes all the ingress packets. And then another XTP program which processes all the egress packets, and which is attached to the VS pair of a container or a VM or any workload, basically. And then we have RPC interface that using a user space program that configures the eBPF maps which are available to these XTP programs, and that's the kind of a very high level core of how Mizar networking works, basically. So that's so just to kind of summarize. So there's a lot of more detail which I'm not covering because due to lack of time, but we'll be very happy if you're interested. We can do a separate session to kind of get into what this is. And just to kind of summarize, the flow programming model is great for programmable switches, but not scalable for multi-tenant hyperscaler cloud environment. And a tremendous provisioning throughput and runtime CPU performance gains using our Mizar network virtualization solution, and it unifies all workload types: VM, containers, serverless, or tomorrow web service, WebAssembly as well. And it has we have additional capabilities such as network policy enforcement, and as I mentioned, our virtualization layer could be easily offloaded to SmartNIC to make it even more efficient. So that's the kind of just to summarize. That was our networking sub-project called Mizar, and then I'm going to briefly touch upon Fornex edge computing project. So Fornex is another sub-project, just like Octos Compute and Mizar networking. Fornex is an open source edge computing framework for managing compute resources on the edge. And that's where, as I mentioned in my very first or second slide, so our CentOS platform is a distributed cloud infrastructure, essentially, whereby you can have independent clusters, including the edge clusters, as part of the overall cloud infrastructure. And our CentOS manages all of these independent clusters seamlessly, And it's designed to solve some of the key edge computing challenges, such as limited computing resource constraints, the heterogeneous resource type, layer topology, the fact that, in an edge environment, you may have a hierarchical topology, So that makes it much more, your scheduling and the whole orchestration makes it much more complex, actually. So that's where Fornex seamlessly addresses all those issues. And then the fact that the reason you're doing edge computing is to have low latency. So that's one of the goals for us as part of Fornex project. And Fornex end users, edge application workloads could be easily deployed in distributed edge, hierarchical edge computing with topologies that best matches the physical and logical structure. I mentioned that before as well. So as a developer, as a deployment person, you don't have to kind of worry about it. Seamlessly provides you abstractions to handle such hierarchical topology. And it also offers high performance virtualized networking for workload communication within and between the edge clusters. So that's a key goal for us as part of Fornex. Computing nodes and clusters on the edge, both computing nodes can run on the edge, and it's summarizing what I said before: hierarchical topology. These are the key features: support for hierarchical topology and flexible flavors. So it's not so you can your edge could be your edge cloud cluster could be based on Octos, or could be based on Kubernetes itself, or it could be based on K3s. So our abstraction seamlessly manages all that. So that's where the distributed cloud infrastructure comes into play. That doesn't matter what type of edge cloud platform you have. Currently, we manage Octos, Kubernetes, and K3s, but our platform can easily adapt to any other edge cloud as well. So edge networking, multi-tenant edge cloud cluster networking by supporting concepts such as VPC subnets and high throughput performance and inter-cluster communication. That's the kind of a key goal. So that's I briefly talked about that. This is kind of a high-level topology. So you have a Octos control plane kind of sits at the top, and then you may have clusters, independent clusters, and they might be in a hierarchical topology. So this whole thing is seamlessly managed by our Fornex Edge Cloud platform. So the last project I'm going to talk about is Altair AI. So this is our AI. So Altair, so as you folks know that AI has two aspects of, one aspect is the algorithm itself. And then the other aspect, which is very important in a hyperscaler, when you're dealing with a large model, big model, the whole system level challenges, how do you efficiently manage a multi-tenant GPU environment or CPU environment? So how do you kind of accelerate, use the acceleration to make the inference better or the training better? So that's what the vision of Altair is. So I'm not going to read through this whole thing, but the key goal is for us to be able to build the system layer, system component that makes the AI vision possible for us, basically at a very large scale. So to be able to do training and inference by having the right underlying system infrastructure to go along with that. So that's Elastic. The key features are Elastic training, dynamic GPU allocation, GPU utilization profiling, resource management, GPU fine-grained sharing, and then the whole parallelism for data parallelism or model parallelism pipeline, hyperparameter auto-tuning, and all of these things. So essentially, all of the relevant system components for enabling the large-scale AI algorithms, basically. So that's the kind of a goal of Altair. Now, what I spoke about is the current state of affairs, what we currently have in CentOS. Now, in CentOS 2.0, there's a major effort going on towards more distributed cloud infrastructure, and that's what we call it, CentOS 2.0. So I'm not going to just kind of briefly touch upon what that is. So as part of the CentOS compute project, so current CentOS is region-based. So essentially all the scalability, 100,000 nodes or 300,000 nodes are at the region level. So our goal of the CentOS 2.0 is customers shouldn't even have to worry about what region they are deploying in. So we call it a regionless platform. It has a lot of challenges, actually. It's not easy. No cloud provider currently does that, actually. Every cloud provider forces you to select a region for deploying your workloads, or VMs or applications. Our goal is, as part of CentOS 2.0, to be able to enable regionless platform by providing the right set of technology set underneath it. Now, quickly, I'll kind of go through that. And Edge serverless computing, and then the new container runtime, which we kind of built out, and I'll talk about that. And then the programmable data plane on the networking side, and the large-scale network simulation. That's very important. On the AI side, GPU profiling, and the data efficiency for AI platform, intelligent optimized scheduling. And on the storage side, we have the cross-region storage, geo-distributed transaction, be able to do geo-distributed transactions. So these are all the things which we are doing. So it's a very high-level compute project now. So the compute, so we have 3 core components of our next generation CentOS 2.0 to be able to manage independent, be able to manage, support regionless environment. We should be able to manage 2 million compute nodes, scattered across multiple clusters, independent clusters. So that's in order for us to enable that, we need to have global resource management, global distributed scheduler, the geo-distributed key value store, which currently doesn't exist, basically, because in a typical edge environment, you need to be able to keep in mind that your network may not be reliable. So how do you kind of do your key value store transactions? So you need to be able to do coordination-free transaction management. So these are the things we kind of looking into. There's a lot of effort going on. There's a bunch of other, and then we have a brand new, the resource constraint at the edge level. You need a very light footprint. So we built out a new container framework we call Quark. And then we have the Edge Cloud serverless framework, multi-tenant serverless framework to go along with that. So, that's, as I mentioned, these are the key components of a regionless global resource services. Not going to get into a lot of detail, but there are a lot of details on our website and the GitHub as well. So these are the things we're working on. KV store. So the current, the only distributed key value, geo-distributed key value store is Spanner. But that requires a very set of very heavy investment. Google did in order to enable a Spanner-like geo-distributed database. But in a typical Edge environment, that model doesn't work. Basically, you need to be able to do coordination-free transaction management across all of these distributed clusters, independent clusters. So that's where we are kind of looking into coordination-free CRDT kind of based approach to be able to enable such key value store. And then that's what I briefly touched upon that. And then we're building out a brand new serverless framework for on the edge as part of our Fornex platform. And then this is a Quark container. So essentially, if you're familiar with the gvisor hypervisor, gvisor the sandboxing open source project from Google. This is on a similar lines, but we have taken that and then we kind of built, enhanced it much more to be able to enable that in Edge environment. We call it Quark. And it has a similar concept of everything is done at the user plane level. And then the whole, how do you do the syscalls basically? So in such an environment, because you can't afford to do syscalls because that's going to affect your performance. So the hypercalls, so that's these are the kind of things, and how do you kind of optimize that? When you do the syscalls outside the sandbox. So that's what this project is all about. Quark containers. It's a pretty interesting project. So that's our container framework as part of CentOS 2.0. And this is Alnair. There's a lot of GPU sharing as part of the AI capability, GPU sharing, profiling, and then the intelligent scheduling and data orchestration. So that's just kind of briefly the CentOS project. We have 7 TSC members. We do our meetings every month, and it's a pretty vibrant repo actually. So there's a lot of work being done. So everybody, I mean, I would like to reach out to all of you folks, and then we will be very delighted to have you folks come and join and and get work with us and collaborate with us and work on all these projects which I briefly talked about. And then every month we have meetings, and this meeting is open to everybody. So it's not just a TSC. Typically in open source, you have TSC members. They control the meeting, but this meeting is open to anybody. So you can put your agenda item in there, and then these are the kind of resources. There are a lot of resources. We have a website, and we have all of these GitHub, and then the meeting notes and all that. Feel free to kind of, I will be very delighted to kind of walk you through if you want to know more about these projects. So that's pretty much it. So I'm going to stop sharing. Thomas, that's pretty much it. Any questions? I'll be very happy to answer.
Okay, thank you, Deepak. That was very interesting. So yeah, CentOS is really a really, really great project. We've already done some collaboration there. It's a really amazing thing, and you should really take a closer look at that. So now we're gonna come to our expert panel discussion. So unfortunately, Professor Weisong Shi could not join us, so we'll be discussing in a reduced panel. So I'm very, very happy to welcome Professor George Pallis. He's an associate professor at the Computer Science Department of the University of Cyprus. His research interests include cloud computing with focus on cloud elasticity and monitoring, edge computing, and big data analytics. He's the scientific coordinator of the Rainbow Horizon 2020 project and editor-in-chief in the IEEE Internet Computing magazine. Welcome. And then I would like to again welcome Deepak Vij. Yeah, you know him already. He is a seasoned technology leader at FutureWay Cloud Lab, formerly chair of IEEE P2302 Cloud Computing Standards Initiative. Deepak has an extensive, successful technology leadership background as technology visionary, board member, and evangelist. With over 25 years of successful technology leadership, Deepak brings to the table a balance of technology vision, team leadership, and strategic vision. His extensive technology background includes areas such as cloud computing, distributed computing, security, predictive analytics, driven business intelligence, security, etc. So welcome, Deepak. And yeah, let's get right into the questions. So yeah, as we've already seen today, edge computing is quite different from traditional cloud computing. So I would like to ask both of you, what is the biggest challenge in the orchestration of cloud edge infrastructures, according to your opinion? And I would like to ask George to please go first.
Thanks a lot, Thomas. First of all, I would like to congratulate you for this organization of this workshop. We hear very nice presentations, and it is really a very nice initiative. Regarding your question, I think that the challenges more or less have been described through the previous talks. I would like to summarize, and I believe that one of the biggest challenges is especially the distributed services, which that can have complex deployment steps with multiple dependencies. For instance, consider the setup of Kubernetes, and you all we know how difficult it is to deploy such services. Also, deploying multiple distributed systems often results in suboptimal resource utilization as we create subsets of CPU, memory, disk, and network resources which are dedicated for each service. So each one of these services is typically over-provisioned in order to account of the maximum load. For instance, you can take an example for Mondays between 8 and 9 a.m. when everyone is working and logging on. You might need 10 instances for a particular service, and the rest of the week, 2 instances will be sufficient. So to be proactive and provision these resources is a big challenge.
Okay, thank you. So yeah, I guess we all know this problem of having these peak moments, and there's a really big challenge in all of cloud and edge computing. So thank you. And Deepak, what do you think is the biggest challenge in the orchestration of cloud edge infrastructures?
Sure, I'm going to pretty much echo what George mentioned. I think so. The whole scheduling, resource scheduling, is going to be very tricky, and it's a pretty complex challenge. You know that, Thomas. So
yeah, we've done quite some work on that.
Yeah, so I think the whole topology, be able to support different topologies, hierarchical topology. And then the whole so now let's say you have thousands of these edge nodes, then you have this application dependency. So you don't want to deploy a workload which is dependent on another workload on one edge, which is far away from other edge. So the whole application dependency has to go along with that. You see. So the whole complexity of topology itself, the deployment topology itself, and then the application dependency. So that makes it even so much more challenging problem. Now the edge computing. Now the edge computing has been around for a while. IoT, but IoT-based edge computing was very static. The workload didn't move. The next generation, the application landscape is very mobile. It's very dynamic, basically. You see. So that adds a new dimension to the challenges, and then the other challenge, mobility. So obviously that becomes a challenge. How do you manage the workload moving from one edge to another? Unlike central cloud, that doesn't happen. And then the fact that even the current edge cloud environment is pretty much around stateless workloads. Now we all know that the enterprise workloads are all stateful. So that becomes very problematic now, you see, because if you have a stateful workload, and you moving at the same time you are mobile, you're moving from one edge cloud to another edge cloud. How do you manage all the storage thing, the state management, for example, you see? So that's, and then the fact that, yeah, you can do replication, but the traditional replication requires transaction, the coordination, some kind of a Paxos or Raft or two-phase commit and those kind of things. You see that you cannot afford to do that because the network is very unreliable. You see, you may go offline, so you cannot do. So there's a lot of things we are exploring. The CRDT, I know Berkeley folks have done a lot of work on that. CRDT-based coordination-free approach, we are looking into that. CRDT doesn't handle all the consistency levels, but it's you know, but there's a lot of other work being done. So we kind of exploring all that. So these are the kind of challenge, and the low location awareness, you know, the mobility aspect, as I mentioned. So it's low latency. The fact that, you know, for example, I have a device, mobile phone on in my hand, and I'm moving from one edge to another. And so it's not just the application workload migration, but I have to worry about my network protocol may change from 3G to 5G to 4G to Wi-Fi. So how do you manage that? So that's part of the equation. You need to manage that as part of your federation as well, though. So these are all there are various other challenges, but these are the challenges we are struggling with actually. See, and we are trying to address that as part of Centaurus, you know, the 2.0 platform I spoke about.
Thank you. Yeah, so we have actually also encountered some of these challenges over the development of Rainbow. You know, the moving of nodes, then unstable networks. So that's all very, very common in edge computing. By the way, if we have any comments from the audience or questions from the audience, please speak up. Don't be shy. Yeah, so in cloud edge clusters, and especially in edge computing, we often deal with a high number of nodes, and simulations and cluster test beds are actually very important for properly evaluating new ideas and technologies. So I have a question for George. How can we adequately and cost efficiently evaluate a new technology that is designed for cloud edge clusters spanning 100,000 nodes without actually buying so many nodes?
Thank you very much, Thomas. And this is a very nice question. And always address this issue since we are working with edge/fog computing environments. Usually, all of us, we are trying to utilize software tools such as simulators and emulators in order to evaluate our systems and algorithms that we developed. But in the context of cloud edge computing ecosystem, we would like to explore the edge capabilities, and here we face new challenges. These challenges are related to application development, infrastructure realization, and performance analysis. So it is reasonable, all these users and all of us to try to find solutions so as to model and analyze the behavior of the fog infrastructure and services. So what we have done in our lab and also within the project of Rainbow, we worked a lot on this, and we developed an emulation framework so as to ease the modeling, deployment, and experimentation of fog testbeds. And if I'm not mistaken, Konstantinos in his first presentation mentioned about Fogify. So Fogify is a very nice tool that can model complex fog topologies, which are comprised of heterogeneous resources, network capabilities, and quality of service criteria. We can deploy the model configuration and services using containers. And also we can experiment, measurement, and evaluate the deployment by injecting faults and adapting the configuration at runtime so as to test different what-if scenarios. Also, we have developed recently another application layer, an extension, so as to be able to support 5G applications and modeling, and this is the 5G slice. Both of these works have been developed within the Rainbow project, and I believe that it is a valuable tool in order to do experiments for instance, we have a digital twins use case, or we have a smart city use case, we can see that with Fogify and the 5G slicer extension, everything works better. And because we are working on this area, we have seen that there is a lot of work that they are trying to be able to develop software tools so as to allow rapid prototyping. And both Fogify and 5G slicer are open source and have been presented in very good conferences. Especially Fogify received the best demo award in SEC conference, and the 5G slicer received the best paper award in IoT TDI conference this year. So we have received very good feedback from the community, and we're working towards to this.
Thank you, George. Yeah, I've seen Fogify in action myself, and it's a really, really amazing tool. So you guys did really great work there. So now, Deepak, during your presentation, you mentioned that you're considering WebAssembly support for integration into Arctos as an additional workload type next to VMs and containers. So I also think that WebAssembly could be a great programming model for the edge environment. But yeah, as with every new technology, there are some challenges. Can you explain some of the challenges that come with this programming model?
Yeah, I mean, definitely, yeah. So WebAssembly does look really good. I mean, so these folks they've really done from Mozilla, actually. I think it came out from Mozilla. And they have really built this programming model from ground up, and they thought through this whole thing, you know, how do you gonna do the sandboxing? So that we are very, very impressed with, I think this is, one of the problems, so if you think about it, actually, you know, all this time, at the end of the day, you know, you run applications, you know, so you that's your final goal. You know, you don't run VMs, you don't run machines. You know, your end goal is to run applications. You see, so until now, the cloud computing, the first generation was in order to we've been kind of emulating, you know, the hardware using VMs, and then the containers came along, and we've been kind of emulating the operating system to be able to enable applications. So WebAssembly is the right model from thought through from a ground up, actually. You see, so that's why. That's why, because it doesn't do OS simulation or hardware simulation. The cold start issue kind of goes away. Basically, it's very lightweight. You see, I have some numbers in front of me. WebAssembly is 100K faster than at cold start. You see. So WebAssembly is 10 to 50% faster at execution time. And as a smaller footprint, the very nice thought through the security model, basically. So these are all the great things about WebAssembly. I think that's what the future of the workload is gonna be. I think that's. But one of your question was challenges. It's not ready yet. So WebAssembly was all about running it within a browser. But then the WASI interface came along, WSI interface, so that you can run your workload outside the browser, just like any application on your server. Now the WASI is there. A lot of effort is being done. A lot of work has been done. It's pretty active. But if you want to port your enterprise application to WebAssembly, you can. There are a lot of things, because you do end up doing a lot of syscalls, you know, storage and networking. None of these things are currently available, actually. So that's one of the challenge. How do you, because they have a very strong sandboxing environment, how do you go out of your sandbox and be able to do, in a secured manner, your syscall, you know, outside the sandbox, you know, be able to do the IO calls, network and storage and other syscalls. How do you do that? You see? So that's, and then you have all of these WebAssembly components. How do they communicate with each other? So that all those things are being currently hashed out, but it's already happening. It's not that these are the flaws, but these are things that are being worked on. So it's not ready yet, but I think these are the kind of challenges we have seen that, so that's kind of a high level summary.
Thank you. Yeah, I think this is a really, really interesting technology that that has come up in the recent time, and I'm also really eager to explore this further myself. So yeah, we have mentioned smart cities a little bit, and we all know that they have great potential. However, there are many solutions out there, many papers that talk about smart cities, and they have great ideas, great concepts. However, I guess we all know it's unlikely that there will be one unified smart city platform that's going to be deployed all across the globe. So how do you think we can provide smart city benefits to all connected vehicles or pedestrians across different cities and countries? George, what do you think?
Thanks, Thomas. From my point of view, the key challenge here is to make the applications so to speak each other directly. Saying this, I think that we need to increase the standardization efforts, which are, I believe, the solution towards to this goal. There are several initiatives, but I think that we need more effort towards this. For instance, we need to have some APIs that will allow the mobile application and the interface with a set of backend services. And of course, we need to have SDKs which so as to provide the core functionality and the ability to gather and transmit the location data. So if we can have these standards and SDK and APIs to the and provide these to the community, then I think that would be very helpful, so we can provide smart city benefits to all the connected vehicles, also to the pedestrian and all the people.
Yeah, that would be really great. Thank you. Deepak, what's your take on this?
Well, I think my take is the same as the cloud, because cloud is going through the same challenge, the whole standardization thing, you see. So you have all these disparate clouds, Google Cloud and Microsoft, and there are thousands of other cloud providers that are coming along, you see. So how do you kind of manage? So there's a project initiated by a lab, actually, brand new lab called Skylab in Berkeley. So they're trying to address that challenge. So we tried to address that, actually. I was the chair of IEEE P2302 initiative to come up with the standardization. So I think that didn't work out. I mean, it was too early, first of all. But even now, the standardization is not the way to do it. I mean, the standard body, it has to evolve from open source itself. For example, your Kubernetes becomes a standard, basically. You see. Your Linux operating system becomes the standard. So that's how it's evolving. And that's exactly the direction the Skylab folks are going as well. So, and one of the example I can give is I'm part of LF Edge, Linux Foundation Edge, a Crano project, and there's a smart city blueprint in there, actually. So these guys, open source, they have created a security abstraction called Parsec, P-A-R-S-E-C. So there are a lot of these kind of things happening, create a common abstraction in open source, and that becomes like everybody uses it, and then that becomes a standard, basically. Just like everybody starts using Kubernetes, and then orchestration, Kubernetes becomes the standard, basically. So I think similarly, that this is going to evolve that way from open source, different platforms, and it will become standard like that. You see. Thomas, you're frozen, looks like.
Yes, Thomas, I think that, or we missed you.
Yes, yeah.
Sorry, I had some connection issues. My internet line dropped. I'm so sorry. Okay, so yeah, thank you, Deepak. Yeah, I personally think that we will need a combination between both formal standards and de facto standards, industry standards. Hopefully, these two will go hand in hand to work out this problem. So yeah, one final question that I would like to ask you. There's a little bit of maybe partly philosophical question and looking a little bit into the further future. So how do you think edge computing could be leveraged to speed up progress in more remote regions or developing countries? George?
Oh, I liked a lot this question. I think that edge computing and fog computing is a critical enabler of a transition to digital-first connected operations. And we have seen many use cases. For instance, we have drone use cases or smart farm agriculture and farming. And all these concepts are, I believe, that would help the developing countries in order to address their problems. Since edge computing increases energy efficiency, reduces latency, and provide context awareness for compute-intensive applications far from the data centers, and increase the viability of technologies. Also, we have autonomous transportations, and I forgot to mention this. So all these concepts can be now be a reality, and we can bring to find solution for remote regions or developing countries. And we have seen many use cases towards this. And also in our project, we have a nice drone use case. So we can see how all these use cases could help these regions and developing countries.
Okay, thank you. Deepak, what do you think?
Yeah, I think again, I'm gonna mention Crino project actually, which I'm kind of involved in it in a different, but one of the member, community member, he donated a blueprint, rural edge blueprint actually. So the two use cases they addressed are the telehealth, okay? So that's essentially you have a doctor sitting in major city, and then you have all of these patients in the rural areas, all the villages and all that. So how do they kind of seamlessly enable such a telehealth kind of environment? You see, you're looking at X-rays and you're monitoring the patient's pulse and all that. So you need very high fidelity kind of video kind of a processing thing at the edge to kind of enable all that. And then the whole rural teaching thing, you see. So you have a teacher, generally in a rural surrounding, you have a teacher and then you have students in the surrounding areas, you see. So when you're doing such kind of a teaching, remote teaching, you don't have to process the video across the, go somewhere miles and miles away and then bring it back. So possibly you can do this video processing at the edge itself, nearby, you see, where the rural area is, and then in a low bandwidth kind of environment. So these are the two challenges. I'm not directly involved in that, but I was involved in reviewing that blueprint as part of a Crino. So yeah, definitely, I totally agree with George. There's so many use cases actually. So especially Edge is gonna enable, the computing in the rural areas where you have very low powered, the internet capability, and such an environment. How do you kind of manage all that?
Okay, thank you. Yeah, I think that edge computing really gives us some possibilities that we couldn't even think of like 10 or 15 years ago. So I think there's a lot of potential in this, and something that really the entire world can benefit of. Okay, so yeah, we have reached the end of our workshop. Thank you very much, Professor George Pallis. Thank you very much, Deepak, for this very interesting discussion. I mean, we could, of course, go on for many hours. I enjoyed this a lot. Yeah, thank you once again. Thank you to the audience for joining. I hope that you could take away some interesting ideas. We will post the recording and the links presented on our website in the next over the next couple of days. Yeah, thank you, and I wish you a nice evening, nice day wherever you are. Thank you.